Cool. So thanks everybody for joining. I'll probably have a few people continue to join as we go, but we should probably get going. So what we're doing here today is a pretty much purely technical webinar. I'm going to talk a bunch about some topics that are, related to service providers and application protocols and some of the things that are kind of tangentially related to Preseem. But we're not going to be doing a Preseem demo. I don't even have a single screenshot of Preseem in this. This is meant to be much more general. The only time we'll really kind of get Preseem-y, if I can make that a term, is at the end. We'll talk a little bit of some of our philosophies and some of the decisions we made based on some of this information. But this is not, again, not in any way trying to be a Preseem demo at all. So what we're going to talk about today is latency, buffering, and the changes that are happening in the transport layer. There's been a lot of stuff happening there that I think it's, kind of that analogy of the boiling frog thing. There's things have been changing slowly. It's reaching a kind of a inflection point, or maybe has reached an inflection point, and I'm not sure it's obvious that that's happened. So that's the broad outline of what we're going to talk about. Little brief introductions. My name's Dan Siemon. I'm co-founder and CPO for Preseem. Jeremy's here as well. Lots of people on the call will know Jeremy from many WISPA activities and many other roles as well. So I'm going to go through some slides talking about these topics. When we do these technical sessions, they won't always be heavily slide-based. This one, I think, benefits a lot from that because we need pictures to talk about a lot of these things. And hopefully the pictures that we've created are going to help explain things and try to get some concepts across. There is a little bit, 2 or 3 years ago, we did a technical seminar at WISPApalooza. The first little bit of the slides are based on those slides. So if you happen to see a few slides you recognize, don't worry, there's a whole bunch of new stuff coming later, but it sets up kind of some background knowledge that we're going to roll into the latter part of the presentation. So high level agenda, I'm going to talk about latency, sources of latency, what latency is, where it comes from, how buffering plays into that, especially how latency and throughput are on tension and how buffering figures into that because it's very, very tight interaction there. Talk a little bit about AQM as a concept, how that plays into that area. And then we're going to spend the rest of the time talking about the changes in the transport layer and the application and the shift in traffic towards UDP on basically residential and commercial internet service providers. And I'm going to use HTTP as basically a kind of a mechanism to walk through the history and say, where it started and where it ended, and hopefully along the way explain why those things happened. Then going to wrap up with a little discussion of TCP acceleration and what's kind of the current reality of the world. Okay, so latency. So what are the common sources of latency? I think if you haven't really sat down and thought about this, it might seem like that the time it takes for information to move from one place to the other is where latency comes from. But in reality, that's just not the case in any networks that, and likely anyone on the call here today cares about. This is basically propagation latency is the speed of light down fiber or electrons in copper. Like this is the speed of light. This is new, unless you invent new physics, you're not going to be able to do anything about this. So if you run a network that spans a couple states or counties or anything less than continents and oceans, propagation latency is just not part of anything you need to care about at all. There's some people
geosynchronous satellite, Dan. That's it.
Yeah. So
yeah.
I guess, or goes to space or something.
Right, they're going all the way to space and back.
Yeah. High-speed traders might do crazy things like run shorter fiber cables in a data center to save like super, super small amounts of time. But for a residential and commercial internet provider, the propagation latency is just so far in the noise. It's just something you should just never really have to think about.
Yeah, for WISP networks, that's absolutely true. There's definitely cases where, like we talked about, this high-speed fiber trading networks where they have moved to wireless, but that has more to do with the fact that when you convert from one medium to another, there's a propagation delay, or there's an unavoidable delay there as you convert between optical and fiber and wireless. So cutting out the conversions allows you to kind of cheat a little bit there, but you can't actually make the signal itself go any faster.
Yeah, and that actually ties into this well. That was a nice segue. I don't that like when the real source of latency is buffering, and medium conversions are kind of an example of that. So if we take a really simple, like let's consider this to be a 3-port switch, and we'll get into buffering in much more detail in the subsequent slides. But if we got 2 input ports and 1 output port, as packets come in, they're stored in a buffer. they move across the back lane or a bus, a PCI bus, or whatever, depending whatever it is, to the output link, and then they're transmitted. The time the packet spends in there, like sitting in the piece of hardware, moving between ports and sitting in buffers, that's kind of like the device's buffer latency, or but it's simpler just to think of it as buffering latency, even though it's like moving across the bus. And this is a perfect example of what Jeremy just said. Like if that was like a copper in and fiber out, that buffering between and making that media transition actually means we have to store packets. And storing packets for any length of time is ultimately where all of the latency comes from in the networks that we care about as residential and commercial service providers. Again, outside of high-speed trading. There's another source of latency, which I just want to touch on very briefly, just because it plays a lot in wireless. There's always this tension between throughput and latency. So a wireless access point may choose to, when it gets a packet, wait a little while in the hopes that it gets another, because then it can amortize the costs of the RF frame. And I'm obviously oversimplifying this a little bit, but it can amortize the costs of the RF frame across multiple packets. And that's good for throughput, right? You're kind of amortizing overheads, generally something that's good for throughput. But that
It's
time
like header
that
compression.
I'm sorry?
It's a kind of header compression in a
Yeah,
way.
yeah, sort of, right. And that time you're waiting, though, that adds latency. So the longer you wait, the bigger aggregate you could form. The less time you wait, the better latency. And getting the perfect thing there is really difficult. And again, just in general, this is a continual thing of the tension of throughput and latency. There's another source of latency, which is much more subtle, a little harder to understand. And we're going to come back to this later because this is really important with some of the transport changes that we're seeing. And that source of latency is loss. But if you think about a network, if you have two packets moving down the link, one gets dropped at the front, that doesn't add latency to the second one. Like that, they're independent events, right? They're not related at all. However, if they're in the same transport connection, you can end up with a situation where the application perceives very significant latency. So I'm going to try to explain that with this little three-state kind of diagram here. So we have on the network, on the left-hand side, we have a network that's representing the state of the network, like the packets that are in the network. The middle column is representing the state of a TCP stack in an end host. And then the far side, the app, is representing what segments, TCP segments, you can just think of them as bytes, it's maybe simpler, have been delivered to the application. So in the first case, the network has been transmitted, or the senders sent segments 1, 2, and 3. Segment 2 has been dropped. The TCP stack at the receiving host has received 1 and received 3. But because TCP guarantees ordering, it can't deliver 2 and 3 until it can't deliver 3 until it gets 2. So the application is stuck waiting with just that first byte or that first segment delivered to it. On the TCP level, there's going to be a signal back, which says, give me, I lost this packet, send it again. Then you're going to have a full round trip time. In this case, just for round numbers, I made it 100 milliseconds. Once that segment moves back again and is passed to the TCP stack, the application has the TCP stack has everything it needs to pass all of the bytes to the application. So although no single packet here ever saw 100 milliseconds of latency, for example, the application perceived 100 milliseconds latency between segment 1 and segment 2. And this is fundamentally why Google has developed QUIC. And we're going to spend a bunch of time in the back half of this talk discussing QUIC. And we'll come back to the slide in a little while as well. So again, a single packet loss does not add latency to the network, but the downstream impacts definitely can. So if packet buffers are why we have latency in packet networks, but what if we just get rid of all the packet buffers? Why are they there in the first place? And of course, they're absolutely necessary to performance in a packet network. And to try to explain why, we'll look at this little diagram here. So a link that's writing bits to the wire, so like copper or physical medium, copper fiber, it's reading bits out of memory, it's writing them to that medium. We don't often think about that, but it is like kind of writing things as it goes. If you don't have any buffers at all, this is column 2, and another packet arrives that's due to be transmitted out that link, then you have to drop that packet, right? There's nowhere to put it. It's just gone. And then you end up in this scenario in the third column where you've now transmitted the orange packet, but you don't have anything else to transmit. And now the link is gone idle and you're wasting bandwidth. And this is fundamentally why packet networks have queues, because you want to have enough things queued up so that you never let the link go idle. Okay, so absolutely fundamentally important to all packet networks. Just has to be there. The problem, though, is if the queues are too big, then they add very significant latency. So this is a simple example with nice round numbers. We have a 1 megabit link. We have 1500 byte, full-size Ethernet packets. Therefore, it takes 12 milliseconds to write that packet to the wire. Okay, just simple math, so we can talk about it. In this case, we've got these 6 blue packets queued up, waiting to be transmitted, and then this red packet afterwards. That red packet is going to have to wait 84 milliseconds to be completely transmitted to the wire. Just sitting there waiting. Those blue packets are not contributing in any way to helping it, but they have to be transmitted first before it gets a chance to transmit. And this kind of concept of packets being stuck in buffers is ultimately where high latency under load comes from. Once a queue gets full, we're backing up these packets into the queue, and we have to wait to transmit them. There's some egregious examples of this. Like a few years back, the Linux still defaulted to 1,000 packets on the output interface. So if you were to put a 1 meg shaper on the output interface with a 1,000 packet queue behind it, you could have up to 12 seconds of latency. So if you've ever done a ping and you've seen those like crazy numbers in the thousands or something, that's like a monster big buffer somewhere that just really shouldn't exist that way. So again, just kind of thinking about this, like consider the user experience when that red packet is taking so long. If that's a packet that's critical to the experience, like a quick DNS lookup or something, then that's not going to be something that makes the end experience very good. There's another aspect, which I won't spend too much time on because this is a little bit kind of complicated, but the way that TCP works is it's always probing the internet to try to figure out what the available bandwidth is. Like there's no way to ask on the internet, tell me exactly how much bandwidth is between point A and point B. I'm going to start sending at that rate. Like that's just fundamentally impossible. So what TCP does is it increases its rate, it observes a drop, it backs off. It increases its rate, it observes a drop, and it backs off. And that's why you get this kind of sawtooth behavior, which you may well have seen in packet captures and things in the past. But what happens if you have really deep queues? Actually, maybe I should back up a second. What it's actually doing there is it's measuring the ability of the network to hold packets. So it sends at a rate up to it sees a drop. And the packets in flight is that kind of measure of what's possible for the network to hold, either actually on the wires or in buffers. And you see more commonly in buffers. And if you have a really big queue, it can end up in this state where it's always sending too much and the queue never drains. The queue just has this like standing queue where it sits at a particular value just below the drop threshold all the time. And in this case, we've got this blue flow putting 19 packets in the queue that is doing nothing to help throughput, but doing great damage to the latency for the green, red, and orange flows. So this one's, again, it's a little bit harder to, if you haven't spent much time with TCP congestion control and stuff to understand, but definitely a real problem that happens all the time. At the end, we could probably point to a couple of interesting and very consumable overviews of this that would kind of explain how that happens, but definitely a phenomenon that exists on the internet today. So these big unmanaged buffers, also known as buffer bloat is the colloquial term for this, is why the internet gets so much slower when a link nears capacity. We've probably all had this experience where you have a link at like 90% and everyone's happy. And at like 92, 93 or something, all of a sudden everything just stops working. Right? Latency goes through the roof. The application stops responding properly. And ultimately what's happened there is we've crossed a threshold where now the queue is starting to back up packets, even on smaller time intervals. And as that happens, latency creeps up, loss creeps up, and you kind of get into this congestion collapse-like scenario. And I think it's kind of interesting that people perceive that as a fundamental thing about the internet, that when the link is at 90%, the service is bad, but it's actually not. It's due to bad queuing on the interfaces that are transmitting into that link. So this is kind of a Goldilocks problem in that you need to have buffers to have a really good throughput. But if you have too many buffers, you get too much latency. And we've been in this scenario for a long time where equipment vendors across the ecosystem, and even really application developers and stuff too, we've been very, very, very focused on throughput and not really measuring latency. And in that world, the buffers just kind of keep getting bigger and bigger and bigger, and latency just keeps getting worse and worse and worse. So how do we solve this problem? And this goes into this whole area of active queue management. So I'm going to kind of give a cursory overview and talk a little bit about it, but not go into a huge amount of detail. But essentially, this is techniques and algorithms for controlling how many packets are in buffers and which packets are in buffers. So the very simplest example is the one I have on the left there, a tail drop policy. This is what most equipment implements. It's the easiest one to do. If the buffer's full, you drop the packet you were trying to put in. So simplest, dumbest, worst from a latency and performance perspective. Another simple example you can imagine is instead of dropping the packet that you're trying to put in, you drop the one from the head of the queue. And this can seem a little counterintuitive, right? Because you think, well, I've already spent all the time holding that packet. Why would I drop it? I've already done work, right? It feels like you're kind of giving up something. But the benefit of this is the loss signal makes it to the other end faster. And then therefore the other end's going to back off quicker. So that's related to like TCP. When it sees a loss, it starts slowing down. Okay. So simple, very simple thing that actually makes a significant difference. One of the early AQM algorithms way back in 1993 is RED. Oversimplifying a little bit, you can think of RED as if the queue's too busy, randomly drop a packet until the queue's not too busy. And basically it's statistically trying to get the flows that are sharing that queue to back off. Tended to not be used too much because there's a bunch of parameters that have to be made just right for the traffic characteristics. And just, it was hard to make it performant, and lots of routers and stuff still have this, but in general, not used a whole lot. And then in 2012, the caudal algorithm was published. So there's an interesting thing in communications ACM, maybe we can link to at the end of this as well, explaining the caudal algorithm. Oversimplifying a little bit again, essentially what you do in this algorithm is you take a timestamp of when the packet was received. And then at the time you're going to dequeue the packet, you look at that timestamp. And if the packet has waited longer than what is a reasonable amount of time to keep the link busy, then you drop it. And again, oversimplifying a little bit because there's some extra behavior in there to kind of deal with TCP and stuff. But the net effect of this is you kind of dynamically size the queue and try to dynamically optimize for good latency and good throughput at the same time. And this is, fundamentally, I think one of the kind of major advances, I'll say, in packet networking in the last, well, it's already been 10 years. It's crazy. I remember the first time I read that. It doesn't seem like 10 years ago now already. But really very significant change that has informed a whole bunch of stuff after it. But I think still probably the kind of state of the art for this as an individual queue management.
So Dan, to go back to your previous illustration of the 84 milliseconds for 7 packets at 1 megabit per second, in this case, the algorithm doesn't have to know how much speed is available. It can just dynamically adjust the size of the queue on the basis of how long the packets are spending. Yeah, so exactly. Okay. Yeah, thank you.
Yeah, that's kind of the fundamental difference. You don't need to tweak a bunch of knobs and match it to the output rate and a whole bunch of other parameters. So really, really simple insight. As you know, the best things are like this, right? It's like someone discovers the right insight that solves the problem at its root instead of a whole bunch of extra complexity. And I think caudal's a really good example of that. And then there's other combination AQMs and queuing schemes that have come after that. I'm not going to spend too much time on this. If you've talked to us a bunch, we can dig into this on more in demos and stuff. But RFC 8920 basically combines fair queuing with the caudal algorithm. So you essentially have a caudal instance for every individual queue, and then you divide flows across that. And this gives you two benefits. It gives you that kind of caudal is going to keep each individual queue low, but even more importantly, this provides isolation across these flows. So one big heavy flow is not going to dominate that queue, create that standing queue, et cetera, and slow down the other flows. And then there's another additional layer added on top of this of automatically determining what's interactive and what's not based on the queue behavior. But fundamentally, this and the things that came with it are just a fundamentally simpler way to solve the problem of network congestion than what everyone tried to do beforehand with application-specific rules and all that other stuff. And we did that in a past life too. So we can come back to the slide. I can expand this more later, but the message here really is there are techniques that allow a packet network to have a great experience under 100% load. And that kind of falls in the bucket of active queue management, and FQ caudal is one example of that. There's Pi, another one that kind of came out of the cable world. The same guys at FQ caudal did one that's targeting at home gateways called QUIC. Some interesting ideas there. Some of them, in my opinion, don't belong in a service provider network, things like the app compression, but there's some really interesting ideas there as well. Okay, so we're going to tie this back now to some transport layer change. And there's some really big things that have been happening over the last while in the transport layer. And I think it's been happening slowly, and it's maybe easy to not understand the significance of this change. And again, I'm going to try to motivate it by walking through HTTP 1 all the way through to HTTP 3. So good old HTTP 1, original HTTP from a long time ago. Each request required a new TCP connection. So you open a connection, you do a GET, you get the body. Okay. This has a bunch of downsides. First of all, you have a whole lot of flows. If you go to a web page with 100 images, you have 100 flows. You also pay the connection creation time, like the three-way handshake for every one of those. The flows spend more time at a lower rate because they haven't ramped up. And again, you have lots of connections. So this is, fundamentally, there's a bunch of obvious problems with this that were addressed, and we'll get to in the next slide. But before I go there, notice this little protocol stack box here in the middle. Keep an eye on that because we're going to kind of show how this stack is changing over time. So HTTP 1, and it looks IP, TCP, and HTTP 1 on top of it. So there's those obvious problems with HTTP 1. Then we got HTTP 1.1. And even 1.1 is a long time ago, right? Like this was the internet for a very, very, very long time. And basically what the benefits we got out of this is we can now reuse a TCP connection for more than one HTTP request. So we can do a get the response, do a get the response. We don't have to create nearly as many connections. It also allowed a simple form of pipelining. So in this example, we could send two gets, that green one and the gray one. And then when the green one is done, is like with the servers made the response, it puts that response on the wire, and then the next one after that. But the key thing to notice here is that this is still incurs a strict ordering. So if that first get is something slow, like a database query, and the second get is a 1 pixel GIF that could be responded to immediately, that 1 pixel GIF is still going to wait behind the more expensive, slower database query. And that's just fundamental to how HTTP works, in that it doesn't have a mechanism to say which responses are associated with which get. It relies on ordering to accomplish that. So big benefit versus HTTP 1 here, again, is you have fewer connections because you can hold it open, but you still have this big head of the line blocking problem where slow resources slow everything else down. And because of that, browsers still opened up more connections than would really be ideal. Okay. I maybe should mention too that what I'm trying to do these little diagrams is the one on the top is kind of time 0, the one on the bottom is time 1. So requests on the top and kind of the response flow on the bottom. So that's HTTP 1.1. So again, the internet for a very long time. And then Google decided that wasn't fast enough, right? They wanted to make the internet faster. Google's all about, every millisecond they can shave off the search page, gets them X more revenue and all that good stuff. So they pushed a thing called Speedy, which eventually became HTTP 2. And HTTP 2 is a beast. It dramatically changes the protocol to be a binary protocol that has framing and header compression and streams, a bunch of stuff that isn't necessarily relevant to the discussion today. So we'll kind of skip that. But the main thing that it does is it solves this head of the line blocking problem at the HTTP level. So we can now issue multiple gets at once, and the server can respond back to those in any order it likes. So in this case, now we see at the top, we have this green get followed by the brown gray one, but the server was able to answer the gray one first. It responds to it, and then the slower get, that, the database call one or the dynamic page load, whatever those things are, they can come down the stream a little bit later.
Yeah,
so
can those responses be interleaved in HTTP 2?
On a HTTP frame basis, yes.
Okay.
Yes.
So if you had one big, like a giant image loading and then some smaller elements, they could be essentially still transferred in parallel, right?
Well, they're in the same TCP stream, so they're interleaved but not parallel.
Right. That's what interleaved. Good. Okay.
Yeah. So you get much fewer TCP connections, or potentially fewer TCP connections. You can spend less time in TCP slow start, like at the beginning of the flow when it's ramping up at speed, and you can basically have flows that just have more data at a higher rate. Again, ultimately the goal here is reduce the overhead associated with many connections and having to bring those connections up. But notice something in the protocol stack. We still have TCP here. And although this solves the problem at the HTTP level, it doesn't solve the problem at the packet level. So on the HTTP level, if the server is able to respond to one resource faster, it's free to do that. But if a packet in the middle is dropped, the whole TCP stream stalls. So I'm going to go right back to that slide we talked about a little while ago, which is this one here. This phenomenon is kind of doomed. HTTP2 is too strong because HTTP2 does have benefits. But because if you think of each one of these, I guess, as like a HTTP response instead of a packet, if one of those packets is dropped, the TCP stack still can't deliver the other resource to the application. So you still have the problem that if there's any packet loss in the network at all, you didn't really solve the head of the line blocking problem. Or I should say,
You're still going to incur some extra latency because you have to do an entire TCP round trip time.
That's right. Like if in this case, again, let's just consider them separate resources. We can't, the TCP stack can't deliver the third GIF to the application until it gets the second one because TCP is an ordered delivery. Right. So we've solved it from the standpoint of the world that the browser sees and the world that the web server sees, but we haven't solved it from like the packet level. Okay. So that's again, there's benefits in HTTP2, but there's still a fundamental limitation there, especially in networks that have packet loss. And every network has some amount of packet loss, but especially when there's packet loss. All right, so where does that lead us? That leads us to QUIC. So QUIC is really, really interesting. It's essentially a new general purpose replacement for TCP. I think this is one of those things where maybe not paying attention, don't quite realize how dominant this is going to become. It's a general purpose transport. It's secure. It was standardized in May of 2021, although it's been used for quite some time. It's now supported by all the major browsers and libraries and extensively used by Google. Like there is a lot of QUIC traffic on your network already. It provides a bunch of it provides all the services that TCP does. So the reliability, the ordering guarantees, provides faster setup. It integrates encryption with the transport layer. So this means that there's basically nothing exposed in QUIC that you can use to identify the traffic, especially in the session resumption stage where you don't have any TLS certificates and stuff. It exposes very, very little to the network. Like unlike a TCP connection, you can see the sequence numbers and stuff. You get to see none of that with QUIC. There's only like 2 fields that aren't entirely encrypted. But maybe more interesting for this discussion is this introduces true transport layer multiplexing, in that we've now got streams that are built on frames, and then streams are in a connection. And this allows one packet drop. Say, for example, here we've got some packet or some streams. So the gray one, the green one, and the red one moving to the right, and then coming back on the left. If one of those green packets is dropped, it has no impact at all in the delivery to the application of the gray one and the red one. So we can now much better within a given transport session tolerate loss. And this makes a really big difference in terms of delivery of these multiple streams and overall web performance and everything else. But one thing I would like to emphasize is that QUIC really is a general purpose replacement for TCP. We're going to see this thing used everywhere. Like it offers many benefits over TCP. Several of them come from the fact that it's implemented in user space, but also just like the services that it delivers to the application. This is going to be, in a lot of ways, how I think most new applications are going to be built. They're going to leverage QUIC. They're going to go away from TCP. It's going to be ages, if ever, that there's no TCP in the network. There's just too many applications that have historical baggage. But this is going to become the standard. Especially, there's now a new datagram mode, which was just recently standardized. So the QUIC libraries can now have a mode where we don't retransmit, but we still communicate there was loss. That's the perfect transport protocol for video and for audio and things like that. No application author is going to rebuild those layers when they're stable and fast and available in QUIC libraries. There's just no point. It's way too hard and way too complicated. Before we jump to the next slide, I guess the other thing to think about is QUIC is designed to be compatible with TCP in the sense that they should share a link relatively equally. So they implement kind of the same congestion control algorithms. That's going to be a point that we'll come back to in a little bit because it's relevant to some of the later slides. So from that previous picture, you can probably get a sense of what this looks like for HTTP 3. So we map each individual HTTP transaction into a stream, And now those streams are entirely split from each other. Again, a loss in that green one doesn't slow the delivery of the red image or whatever that is to the end application. Very powerful from that standpoint, from a loss standpoint. This has just been published as a standard. There has been HTTP3 and QUIC traffic for some time, but this was only published as a standard just a couple months ago in July, supported by all the major browsers and library vendors. Leverages QUIC streams, as I mentioned, for each individual HTTP request. And even going back to 2020 in October, 75% of Facebook's traffic was QUIC. I mean, 75% of Facebook's traffic was UDP in your network. And I think that's what I mentioned earlier about this. It's kind of been like a slow boil where all these things have been moving to UDP. But if you think about what we're taught in like networking classes and stuff, we're taught that this is slightly overstating it, but all the important traffic is TCP and UDP is not important. We're in the opposite world now. All the new applications are using UDP and they're layering QUIC on top. Okay. So this is what the protocol stack looks like. IP, UDP, QUIC, again, as the new kind of, I think will become a very dominant transport protocol, and HTTP3 on top of that. Okay, so lots of change, and I hopefully that helps to motivate why QUIC came about. But again, just to reemphasize, it is not tied to HTTP3. Like lots and lots of applications are going to end up using QUIC as their transport protocol. So this leads us to our last topic, which is TCP acceleration, and something that we decided a long time ago we weren't going to do. And I'm going to try to explain a little bit what this is, and a little bit why that's the case, and we'll tie that back to the other thing, to the other topics we've been talking about. So what is this? Essentially, it's a TCP transparent proxy. Like you may call it an accelerator or whatever you want to call it. It's really a transparent proxy. Looking at the left-hand side, so a normal situation is you have a TCP connection between two end nodes. You have node A and node B. They hold the state for the connection. They control the transmit rate, the congestion window, the retransmission policy, all that kind of stuff. The network in the middle really doesn't know anything about it. When you introduce a TCP proxy, you split that in two. You have a node that's node A talking to the TCP accelerator. It thinks it's talking to B, but it's actually just talking to the middle box. And then likewise on the other side, B thinks it's talking to A, but it's actually talking to the middle box. So you can completely split this. In a lot of ways, you can think of this as kind of like a NAT, in that it introduces state in the network to run these different congestion algorithms, or a different state on each side. So it says all the downsides of a NAT box, in the sense that if the traffic needs to bypass, like if you have a failover link and it needs to take another path, all the TCP connections have to die. Or if you have like a redundant, an OSPF path to bypass the box, you can't just fail traffic over to the other path in the middle of the day, because all the TCP connections die, and customers are going to notice that, right? So that, and in general, you just don't want to have too much state in the network, and this is another example of state. But why do these things exist, even historically? And really, what this comes down to is you can implement different behavior on each side. And in certain scenarios, that can be interesting. So if you have a geosync satellite and you've got a lot of latency and you want to hide that latency, implementing a different congestion control algorithm there can be really interesting. If you have a slow link or a link that's lossy and you can't fix it, you should really go, like, the real answer is to fix it. But if you can't fix it, then having TCP, a different TCP retransmission policy can be useful in that case. But I'd argue that none of those scenarios exist in a modern access network. They don't exist in, I'll define that for now as like a residential and commercial network in the United States, for example. We don't have those low bandwidths, and we don't really have the situation where we can't fix loss, or we shouldn't have the situation where we can't fix loss. So what does this mean for us? So, well, not for us, but our opinion of this and acceleration in general. Even in a past world where TCP is dominant, and this world doesn't exist anymore, like, right, so much important traffic is now already QUIC and HTTP3 that this world just doesn't exist. But even in that world, there's still lots of downsides to this. I mentioned the state in the network, not being able to fail over. And then just as a general networking principle, you don't want to have too much state in the network if you can avoid it. Of course, some cases we have NAT already. You got to do what you got to do. But in this case, you don't really want any more. But there's another thing here that I think is much more subtle, and I'm not sure I've really been able to I'm going to give this a go. I'm not sure I've got the perfect way to communicate this yet because it's really, really complicated. But it's really easy to make TCP throughput look good by crowding out other types of traffic. All you have to do is be more aggressive in your congestion control and how quickly you do retransmissions. And I kind of know this from experience because way back in grad school, I built a TCP stack that was for some research stuff we were doing. And that was able to transfer it to Linux. It wasn't production quality, but it was able to transfer it to Linux stack at gigabit per second and stuff. And it's really not that hard to write a TCP stack. What's hard is to do TCP congestion in a way that's fair. And this is an area of 1,000 PhD theses. This is where Google spent 10 years building BBR and BBR2, TCP Vegas and Reno and QUIC and all these things. These are all attempts at finding the perfect congestion control algorithm that gets you good throughput and plays fair with everything else. And this fairness thing is the really tricky part. So we're going to try this scenario of, let's consider an access point that's operating at full capacity. And maybe I should have even made that just like a 50 meg, nice, clean backhaul link, because then it takes the complexity out of the access point side of this thing. But it's operating at capacity, right? It's full. There's no free capacity. Anything that's done to make TCP better is necessarily making everything else worse, right? This is a zero-sum game. If you're gonna optimize TCP and make it faster, that bandwidth has to come from somewhere if that link is already busy. And again, it's really easy to make these to create a congestion control system that is more aggressive in retransmissions and makes an Ookla speed test look faster because that's a TCP flow, or maybe makes Netflix look faster because Netflix is still TCP today. It won't be forever. They'll switch to QUIC eventually too, but they are TCP today. It's not hard to make that happen. But if you're not at the same time measuring the impact to everything else, the net effect will actually be a worse customer experience. Right?
Or it's not going to be consistent across all of your customers. Like, there's no possible way to predict exactly what a customer will want to do at any given moment.
Well, or which protocols and which traffic is actually important to them.
Right.
So in a world where all of Facebook is UDP, if we've made TCP faster and shrunk UDP, have we made the customers happier? I would argue that at least we don't know. And the answer is probably not.
Probably not. Yeah.
Yeah.
And I think there are specific cases, Dan, where, let's say you have a particular business customer that wants to prioritize a certain type of traffic on their network. That's absolutely relevant for that business to do. But my opinion is that that's past the demarcation. That's not a core network operator function, because we have no way of knowing, in the moment exactly what traffic is going to be important to somebody. We had a question in the chat about how do we determine which TCP sessions contain real-time traffic. He says, well, firstly, they're probably not TCP if they're real-time, and secondly, we do that based on flow behavior. I don't know if you'll get to this, Dan, but just it seems relevant here, where the best thing that we can do today is not prioritize one particular type of traffic at the expense of another.
Yeah, we could maybe dig into that a little more.
Probably in the discussion. Yeah.
We'll try to keep this at a high level conceptual, not too Preseem-y, but if we can go there in a little bit. Yeah. So this is kind of one example, but even just take another thought experiment that if TCP's congestion control and QUIC's congestion control are designed to be compatible, right? They behave roughly the same and they should share a link equally. If you have an access network that needs TCP acceleration to make TCP deliver a good experience, it's guaranteed that QUIC is not getting a good experience.
Right.
Because you can't make anything that's entirely encrypted like QUIC. You can't do a middle box. So if a network requires TCP acceleration to make Netflix happy, guaranteed that the YouTube QUIC traffic is already in pain because it's seeing all the same packet loss and retransmissions and everything else the TCP connection is, and there's no way to fix it, right? So we'll get into the next slide, kind of our philosophy on this, but you can probably get a sense of where that's going. And this is probably the part that's a little bit of personal opinion, but I just don't think TCP acceleration really belongs in a modern access network at all. And HTTP3 and QUIC, and again, modern access network, I'm saying, maybe I should have just spelled that out, like a residential commercial access network,
low
in
latency,
the US kind of thing, or like somewhere else with a decent bandwidth. Yeah.
Right.
HTTP 3 QUIC just put the nail in the coffin, right? Like there's so much traffic is going to be in that protocol now that if you're relying on TCP acceleration for a good experience, you're just setting things up for a net negative experience across your customers.
Or at worst, or at best case, a continually diminishing enhancement, because as traffic
that's
moves
right. Because
off of TCP.
the volume is going down, and the importance of the TCP traffic is going down. Like all of the major apps are switching to QUIC. So these are the apps your users care about the most, and now they're not amenable, for lack of a better term, to any type of acceleration. So if you're going to go down this path, I think it's really important to at least figure out a way to measure the damage done to non-TCP. And I've never seen anybody be able to do that. Okay, so this is kind of the only Preseem slide. So we get asked once in a while, will we do TCP acceleration? I think you can probably guess from what I've been saying that the answer to that is no. But really what this comes down to is our goal is to help our customers have a clean access network that delivers a great experience for all applications. And this is fundamentally why we also don't want to do DPI and application-specific rules. Because if your customer experience relies on prioritizing Netflix, what about all the other things that aren't prioritized? Right? Like we need all of the applications to get a good experience all the time. And TCP acceleration falls directly into this. Like all this high value traffic is now no longer TCP. If we rely on TCP acceleration to make that better, we're papering over the underlying problems in the access network that we should just fix and make everything better for everybody. And we don't need all this protocol and application specific complexity. So that's kind of the only, Preseem part. I guess, in our minds as well, like quality of experience isn't just traffic management. DPI, that kind of shaping, and TCP acceleration is traffic management. It's not just quality. That's not what measuring and improving the quality of experience of a network actually is. So we're going to move to questions in a second. I think we're at a pretty good time, 40 minutes in. But before we move into any questions or longer discussion, if you're going to Wispapalooza, I guess it's only like a week and a half away already. We're hosting an open house on Monday from 2 to 4. You can get the QR code here. We'll follow up with an email after the webinar for everybody that attended as well, with just kind of a link. Come by, grab a drink and leave, grab a drink and chat with us for a while, grab a drink and talk to your friends, whatever. But I'd like to encourage everyone to come by. We could talk about stuff like this. We can show you some of the new things we're working on, or we can talk about the weather. But you're welcome to come by and say hi. So. All right. And with that, I have not been following the questions at all. So Jeremy,
so we haven't had a ton so far. I think we've mostly answered the ones that have come in. But I want to start the discussion off. I've got a couple. One is more like a question or a statement or a contribution to the thought experiment about not just about TCP acceleration, but about quality of experience in general. And then the second is I want to get into that latency measurement part, because this would feed into the measuring the damage. So the first one is, so the thought experiment I've applied, because I have operated networks where TCP acceleration was an absolutely essential part of delivering any customer quality of experience at all, specifically geosynchronous satellites. These heavily constrained, where just dealing with the round trip time, that that pure physical distance, because TCP is not optimized for latencies that exceed really just a few tens of milliseconds, to be honest. And perhaps we'll see some things at the transport layer improve that, but right now the advances that we're seeing in satellite are the move to low Earth orbit, which eliminates that long delay anyway. Kind of puts us almost right into the WISP category in terms of just the propagation delay itself. So when I think about adding a feature to, let's say, Preseem, because of course that's what we deal with every day, the question is that I come at with my operator experience is, can I sell this as a feature to my end users? So on the one hand, we can say, hey, we can maybe sell with TCP acceleration. We can sell prioritization of a particular type of traffic, say whether it's Netflix or whatever. We want to have this streaming experience be perfect. But the downsides, as Stan said, are that you have essentially uncontrolled second order effects, where you now no longer have really a clear grasp of the quality of experience on that network overall, which in the long run, it seems to me to be far more critical than can I make my speed test look good in the short term? And so I think, can I sell this as a feature? So, even if we're talking about optimizing any specific type of traffic, history has shown us, because I've been doing this a long time now, history has shown us that
How long, Jeremy? Yeah.
well, since the 90s, so
Yeah.
not quite 30 years, but over 25 years. Um, History has shown us that the traffic that is it's the thing that people are buying internet for today might not be the thing that people are buying internet for in 5 years, right? So I think about it from a return on investment business owner perspective as well. Do you have any counter arguments to that, Dan?
No, I think there is constrained situations where transport layer or protocol specific things can have value. Like if you're, I don't know, an enterprise that needs like one particular custom application, always prioritizing stuff. Those are real use cases. They're just generally not. They're almost always not residential / commercial use cases. Like
Well, and I
that's
feel
kind of more of
they
a
should generally be handled at the edge. I mean, some exceptions
right.
to that might be something like
Yeah.
if you're running a Metro E network and you're providing carrier backhaul to a cellco. But in those cases, what you're providing them isn't internet. You're providing them a completely
Yeah.
different type
Right.
of
You're giving
service.
up a pipe at a particular
You're
rate.
giving them
Right. Yeah.
exactly, and usually it's on them to deal with the application side of it. So that keeps that complexity entirely out of the ISP network, which is how you can keep it affordable. So the second thing I wanted to know about is we're seeing this this continual deprecation of TCP, and we talked about how there will be this likely long tail. So when we talk about measuring the damage to a network, or measuring the loss and the latency that's being incurred in that network, we are using TCP. So what's going to happen as that tail drops, Dan? Like, are we still going to be able to continue to measure latency?
Yeah. What Jeremy's referring to is we leverage some TCP headers to get kind of fine grained TCP latency, like the sequence numbers and stuff, and that gets harder in a world with QUIC. Fortunately, for the use cases that we're using that for, which is kind of like measuring the health of an individual access point, et cetera, you actually don't need a whole ton of samples to be able to say something intelligent, right? You don't need to have like constant samples. So I think it'll be a really long time before we don't have enough TCP for that to work, like probably like a long time. But there's some tricks we can do there too. Like even on the UDP side, like measuring the time between like when a flow is idle, a packet goes by and the response packet comes back. Those type of things are still going to give us the ability to get some sense of the underlying latency that's going through those links, maybe at a slightly less granularity depending on the volume and stuff. This has really been an interesting thing. Like if you read the QUIC standards, there's this thing called the spin bit. And the spin bit is designed to allow intermediate devices to measure the latency. But there's kind of two views on this. The one view is, well, that's a useful tool for the operators. And then the privacy view is, why are we letting the internet provider see anything at all? We're just going to encrypt the whole thing. They just move bits. Like stop looking at this kind of stuff. And although that spin bit made it into the standards, Google is very much on the privacy side, and they just don't set it. And I mean, from a practical standpoint, if Chrome's not setting the spin bit, it's kind of effectively useless because Chrome is just so much. I mean, Firefox doesn't do it either. It's just so much of the overall internet traffic. So yeah, the long tail. There's going to be some other techniques needed to kind of measure that. There could be some underlay things too, I think, which are super interesting. But for the use cases that we're using it for, we're a long way away from not having enough samples to make use of that.
There's that old saying which says, the internet sees censorship as interference and routes around it. This is you could think of any type of operator, an operator's ability to identify what their customers are doing on their network are absolutely, that's going to be considered a type of censorship. And as we can see the trend moving forward, that we as operators, and I put myself in that bucket. I still run networks. We should expect a world in which ultimately a customer may come to us and say, can you identify a particular type of traffic? And we're going to have to say, no, we can't, because the endpoints are moving to protocols where they want the ISPs to have as little visibility into this traffic as possible, and there's little ability to interfere with what they're doing as possible.
Yeah, like that's an explicit design goal of QUIC. Is like,
Yep.
don't let the operators understand
know
what
anything. Yes,
Yeah.
correct. Which it
Yeah.
does have the added benefit of increasing the security of your traffic as it goes across the internet. You
Mhm.
like I'm less concerned about malicious ISPs because I know ISPs. We don't have time to be getting in people's business, right? It's that if we have vulnerable systems at our ISPs that can be hacked by foreign agents. I mean, we've seen attacks like this globally, for 20, 30 years. So we should expect those hacks to continue. Attempts on our national security, if you will. But we should also expect that the folks who are putting bits onto the wire are going to continue to try to prevent any possible breaches. We've got a question from Larry. How are things going with measuring latency on a 450M? Perhaps that we would be improving that. I'm trying to think, is there something specific about the 450M? Maybe
I don't.
withdrew the
Yeah, I
question.
mean, probably what that's alluding to is that the kind of the sub slices and being able to identify which
Yes.
of the individual slice. I mean, different terms are used for this thing all the time for which individual slice is
Spatial
congested.
streams. Yeah.
No, we don't have anything to share on that yet.
Yep.
It's something we've looked at a bit, but it unfortunately it hasn't really made its top of the pile. And there's some interesting problems in getting that information in a way that's useful.
Yeah. Probably
But
not
in general, I
technically
mean,
impossible, but possibly not worth the
yeah, like
squeeze.
I mean, we have some things
Definitely.
that we thought about doing there. I mean, we could do some analysis. We get a lot of latency samples and kind of determine from the latency profile which people are in which slices and if there's a busy slice, even outside of getting any signaling information
Yeah.
back. I think that's likely possible, but we haven't been able to, or we haven't made any progress on that yet.
Yep. Absolutely. No additional questions so far, so we might be moving toward a wrap up. Get your questions in if you have any last ones. Yeah, Dan, this has been a fun discussion. I know I've been following the HTTP 3/QUIC progress because as Dan pointed out, it's been in use in networks for quite a long time. Since all you need to be able to do is use an existing transport, in this case UDP, and then write some additional layers on top of it. And particularly in the mobile world where it's very easy to deploy applications to a huge swath of users very quickly, there's been able to be a lot of testing, both on they call them the mangas or the fangs, the big companies, and
Yeah, and I think what you just said there is actually really key. Changes to TCP were slow because the OS had to change. Changes to QUIC are fast because you just have to update Chrome.
really there isn't any practical time frame on which to make changes to TCP because there are
You
so many so many
so many middle boxes.
so many middle boxes, so many routers throughout the entire
Yeah.
internet that rely on specific functionality of TCP. It's just really not practical. This is really the only way to move the internet forward is to move away from legacy protocols like that.
Yeah, and that, as I mentioned, QUIC was designed to block the providers. That was actually not what it was actually designed to block is middle boxes. They did not want to end up in a spot where there would be middle boxes introduced to the network that would slow down the evolution of QUIC. So by encrypting everything, middle boxes are just impossible.
Well, I want to point out that we still provide quality of experience on QUIC.
Oh, sure. Yeah.
What we don't do is measure the latency on it
Yet. And
yet.
it doesn't, yeah, that's kind of orthogonal to some of the other stuff we've been
Yeah.
talking about. But yeah, that's right.
Yeah. Okay, we've got a question from Larry. Do customer-owned routers have the ability to change TCP or UDP priority? This kind of sounds like a little bit about maybe DSCP markings.
So that like conceptually, that's certainly possible. I don't know specifically which ones do,
Yeah.
but they could definitely, or if you're asking if they have the ability to influence us, that's not something we do today.
No.
There's some ideas that would be an interesting webinar to talk about there. But DSCP marking is kind of one possibility to do that, to change the network treatment, or they ultimately, like if they were to queue smarter themselves, like
Right.
every CPU radio in every house should have a decent AQM, right? There should be decent AQM on every link of every hop everywhere. and we're just going to be, a decade or two away from that happening, because we have to upgrade all these devices. They have to get smarter. We have to get faster chips,
Right.
all that kind of stuff.
In general, that's obeying DSCP markings that's a business functionality. You don't really see customer networks. Usually they're just discarding those tags at the edge, and they're not really doing any type of priority based on customer traffic markings.
Yep. All right. Jason's question there. Yeah, I think the YouTube page is probably the best thing for videos sort of like this. If you're looking for specific kind of training videos on how to use Preseem and stuff, then you just kind of reach out to us and we can hook you up with something there. And the last question there is, do you need a new network card? No, QUIC is just, from the perspective of the network, it's just another application on top of UDP. That's all it is. So when Google started rolling out QUIC into Chrome, it was just a Chrome update. And now all of a sudden, all the Google traffic switched from TCP to UDP. Same with Facebook. The Facebook app switched to HTTP3 and QUIC. Same thing happened. No change in the routers, no change in the network card, no change in the operating system. Just update the software.
Right. Yeah. Let's see. Any more new ones? We had one about the videos. No, I think we're good. We should probably wrap it up.
Perfect. 4 minutes left. Well, thank you, everybody. Hopefully I didn't make things more confusing than they were already. Some of these topics are a little confusing, but hopefully that was interesting. Feel free to send us an email, Jeremy or I. We maybe can put some contact information or something in the email that follows this. If you have any questions, and if you are at Wispapalooza, come on by, say hi. That'd be great.
Or come by the booth if you can't make it on Monday. We will have a big booth in the center, and we've got lots of people there. Please come by and hang out with us a little bit. So thanks a lot.
Yeah, thank you.
435. Angie says, booth 435.
Awesome.
Thanks,
everyone. Thanks for attending.